In this video, we shall concentrate on the necessity of counter form of rational numbers by assuming only rational numbers exist. Are we going to miss some numbers if we consider only rational numbers? Answer to this question is yes. In fact, we are missing infinitely many numbers. How can we observe this? Let me ask a question. Is there any rational number whose square is 2? If yes is the answer, if no is the answer, I don't care. If yes is the answer, then the equation p square is equal to 2 must have solution in rational number set. If there were such a p, then we can write p is equals to m by n, where m and n are integers that are not both even. Why we are imposing such conditions on m and n? Let us see what happens if both are even. If both are even, we have the cases like n divides m, n not divides m divides n, which is a case of reciprocals. Neither m divides n nor n divides m. Case 1, both are even such that n divides m. Here p becomes an integer. For example, m is equals to 4 and n is equals to 2. 4 by 2 gives you 2. This type of rational numbers, I mean integers, cannot be our p since there is no integer whose square is p. Why do you think so? Do you have any idea? Please do comment on that, or please do comment your idea also. Case number 2. Both are even and n not divides m. Here we will get a simplified rational number where at least one of the numerator or denominator is odd. So in this case, our m by n is simplified to our condition imposed on m and n, that is not both are even. How? Let us see example. M is equals to, take m is equals to 8, n is equals to 6. 8 by 6 can be simplified to 4 by 3. Here look the denominator. In the denominator we have 4 by 3, that means a denominator is 3. Here n is odd. Similarly, m is equals to 14 and n is equals to 6 will gives you 7 by 3. Both m and n are odd here, both the numerator and denominator. Case number 3. Both are even and m divides n. I don't explain this case. This is very easy to understand and see that p is simplified to a rational form which we are discussing. See this example. M is equals to 8 and n is equals to 16, which will ultimately gives you 1 over 2. This is a case of reciprocals. In every reciprocal, numerator is odd, so that is 1. Case number 4, both are even and neither m divides n nor n divides m. Just read out what is here. It is just like a case number 2, and if you want example, the same example which we used in the case number 2 applies here also. In every case where m and n are both are even, our m by n is simplified to our condition imposed on m and n, that is both are not even. Sorry, not both are even. Thus we can write, if there were such a p, that is we are talking about a rational number whose square, rational number p whose square is equals to 2. If there were such a p, then we can write p is equals to m by n, where m and n are integers that are not both even. So it will gives you p square is equals to m square by n square, which is equals to 2, because p square is equals to 2. Then m square is equals to 2n square. So yeah, now we are looking m square as a multiple of 2, therefore m square is even. I'm stating one statement here. If if m square is even, then m is even. Let us see how. We have to prove here, if m square is even, then m is even. For this we shall prove this. We shall prove it's a contrapositive statement, that is m is odd, then m square is odd. Proving a statement is as equivalent as proving the contrapositive statement of it. What is the contrapositive statement? If P is true implies Q is true, then the contrapositive statement of that statement is Q is not true implies P is not true. So even is it, if even is a condition of true, then odd is a condition of false. If M is odd, M square is odd is the contrapositive statement of if M square is even, then M is even. If M is odd, we can write M is equal to 2x plus 1, where x is some integer. Then M square is equal to 4x square plus 2x plus 1. Here 4x square is odd because multiple of 4x square is even because multiple of 4 are even, and 2x obviously even plus even is even, then 4x square plus 2x plus 1, so even plus 1 will gives you odd. Hence we can conclude that if M square is even, then M is even. Now we have M square is equal to 2n square, thus M square is even, thus M is even. So we can write M as M is equal to 2 into Y, where Y is some int, or you can take in the place of Y you can take X also. M square is equal to 4x square is equal to 2n square, which will this is because M square is equal to 2n square, and therefore we can write n square is equal to 2x square also. Then n square is even. Similarly, n is even. If you don't understand why n is even, please rewind and see why m is, because we actually explained this where we are explaining why m is even if m square is even. Now let us see how things are going. We took p as p is equals to m by n such that m and n are not both even. Now we are getting m is even and n is even because we just saw that we got m square is even, therefore m is even. Similarly, n square is even, therefore n is even. So our m and n right now are even. This is a contradiction because our m and at least one of the m and n should be odd. So our assumption p square is equal to 2 has solution in Q is wrong statement or wrong assumption. Thus, there is no rational number whose square is 2. This discussion alone don't satisfies the questions like does such kind of number exist? If they are, where are they? And etc. We shall deal them in the next video. Until then, let me know, or you just comment how you will find the answer to this question. What is the length of the diagonal?